Okay, so I wanted to go over a couple things. We talked a little bit about notation on Thursday. I mean, you know what the day was. Last time I saw you. Okay? So those of you who really like English, here's some, it's grammar for you. dy dx is a noun versus ddx is a verb. Okay, so when I give you dy dx, it means the derivative of y with respect to x. However, when I give you d dx, it means take the derivative with respect to x, and something will be following it so you know what to take the derivative of with respect to x. Okay. So dy dx is the derivative. D dx is take the derivative of whatever is following it. Okay, now there was a problem in your homework. Okay. Caroline pointed something out to me before class. F of x equals 7. She's like, Mrs. Hellman, do I really have to do the algebra for that? F of x is equals 7. What does that look like? Horizontal line. What's the slope at any point? 0. What's the derivative of any horizontal line? 0, okay? So if we have a constant, horizontal line, we have a constant, the derivative anywhere is going to be 0. That's something that we can know, all right? So here is this put into action here. So the derivative of any constant is 0. If y equals a constant, dy dx is 0. Those are your two different notations, and you can see how they work. All right. So, derivative graphs. A graph of a derivative represents all of the slopes of the function over a domain. So if we take all of the slopes from all of the infinite points on our graph, we can create a derivative graph. So if we graph the derivative, it represents all the slopes over the domain. So our warm-up problem was y equals x squared, right? And our derivative was 2x. So if we graph 2x, that just represents all of the slopes from our function y equals x squared. Now, I want you to just sit back. I'm not going to say relax. I want you to focus, okay? But I'm going to go through some graphs here, or a graph, and I'm going to point out some tangent lines, and then we're going to look at what that derivative graph would look like, okay? So here we have y equals x squared. That's what we had in our warm-up problem. We already figured out that the derivative was 2x, okay? If we look at the slope at x equals 9, okay, our slope is negative 18. So on our derivative graph, we have the coordinate -9, -18, because -18 is the slope at -9. If we look at x equals -4, our slope is -8. So on our derivative graph, we have the coordinate -4, -8. At x equals 0, we have a slope of 0, okay? That is our kind of change in direction. So we have slope of 0. So on our derivative graph, we have the coordinate 0, 0. All right, this is going to start getting redundant, I know. Okay, so this is what I want you to think about. When are we going to have positive derivatives versus when are we going to have negative derivatives? Think about what a graph would look like and how do we know one versus the other. I'm going to give you about 30 seconds to discuss with your group. Positive derivatives versus negative derivatives, how do we see them on the graph? Okay, that sounded like a very quick conversation. I got like quiet all of a sudden. Pod 1, what do you think? Okay, on this example up here? Why? Okay, and on the right side of the graph, we have positive ones. Okay, so in general, like if I were to give you any graph, Pod 2, what characteristics would we look for positive versus negative slopes? If it's rising or falling. Okay, so if we had a section of the graph that was rising or increasing, what kind of tangent lines would we be drawing? Positive. If we had a part of the graph that was falling or decreasing, you could say, what kind of tangent lines would we be drawing? Negative. So Henry, that's why this is the left versus the right, right? Pod 1. Because we are decreasing on the left and then we are increasing on the right. Okay? Decreasing, those x values gave us negative slopes. Increasing over here on the right, we could draw positive slopes. All right? If your function is increasing, no matter what kind of function it is, you will have positive slopes for your tangent lines. If your function is decreasing, you will have negative slopes for your tangent lines. And we talked about the case of a function that is constant. Okay, we know that derivative would be 0. Okay, so how is this going to help us? Okay, I'm going to give you the task of either coming up with a derivative graph or matching derivative graphs. Okay, probably the biggest thing you're going to have to do is all right. So if we see we have a function that's increasing, that means negative derivatives. Well, for that part of the domain, your derivative graph should be under the x-axis because that would be negative derivatives, okay? If you have an increasing portion of your function, well, those derivatives are going to be, did I just say that backwards? It's the wrong one. Okay. If you have an increasing portion, then you know your slopes are going to be positive. So the x values where our function is increasing, then your derivative will be above the x-axis because your derivative values are positive. Okay? Let's go ahead and look at a couple examples. All right? Here is one that we already saw, right? This is the one that we talked about. So we are decreasing from negative infinity until 0, which means we're going to have negative derivatives. You see that we have y values below the x-axis for our derivatives because we have negative derivatives. Okay? Here at 0, we have a nice smooth change of direction. Okay, remember, corners, our derivative is undefined, but a nice smooth change of direction, we would have a horizontal tangent line there, which means our derivative is 0. Okay, and then as we increase, we have positive values. Okay, let's look at a different one. Okay, here is our function. Okay, notice how it is increasing the whole time. Our derivative is always above the x-axis. Okay? The only thing that happens here is we do have a horizontal tangent line at 0, which means our derivative needs to be 0. Look at that. Okay? Now, some of you were noticing some patterns when we were looking at polynomial derivatives. How many of you are noticing patterns with polynomials and their derivatives? Okay, as far as their degree. Okay, some of you are starting to notice some patterns. That can be helpful here when we're looking at graphs. Okay. I do have another one. All right, here's another example, and then I have some for you to work on. Okay? So I would say from negative infinity to negative 4, our function is decreasing. From negative 4 to a little past 0, we're increasing, and then we're decreasing, and then we increase again. Okay? So I have 3 times where my function has derivative of 0. Notice those smooth turning points? We're going to have horizontal tangent lines. So that should correspond to 1, 2, 3 places where my derivative is 0. So it crosses the x-axis. Okay. We'll talk later about these points being relative minimums and maximums, which is a term that you talked about last year in pre-calculus. That's nothing new. But those are going to correlate with x-intercepts here on our derivative graph. Okay. We are decreasing up until negative 4. Notice how we are below the x-axis up until negative 4. Okay, we increase from negative 4 until a little past 0. We are above the x-axis from negative 4 up until a little bit more than 0 on our derivative graph. Okay? Where the function is increasing, the derivative is positive. The function is increasing, the derivative is positive. Okay? As long as your derivative is, or as long as your function is differentiable, right, you shouldn't have any discontinuity. Nope, I'm going to take that back. No, I am. As long as you have a nice smooth curve, right, for your function, you should have something smooth for your derivative. Where we get into trouble if we have like a point of discontinuity, like with the absolute value graph, then you're going to see some, like a jump in the derivative graph. Okay? So, I'm going to give you 4 graphs and 4 derivative graphs. I'm going to give you about, I don't know, 1 to 2 minutes to match these up. I think 1 would be enough, but we'll see if we need to. Hey, it is quiet in here. It's not supposed to be quiet. You're talking to each other.
If you go from left to right, be positive until you get to 0. And then you're like looking at the graph of 1, you're going to be positive slope until you get to 0. And then you're going to be negative until you get to 2. And then you'll be positive. So if you look at B, it's positive y values until you get 0. And then you get negative y values until you get 2. And then you're back right.
Okay, raise your hand if you need more time. Okay, pod 6, what does graph number 1 match with? Okay, can you give me a couple highlights as to why?
The B graph, it like fits in the pocket there on number 1.
From 0 to 3,
yeah,
it's decreasing, and on 0 to 3, the graph is below the x-axis.
Okay, from 0 to 3, we're below the x-axis for the derivative, which means we should be decreasing on our original function. That's very good. Thank you. Pod 5, give me 2. That's you guys, Amy and Will and Michael. Can you tell me why? Like, how did you know to match that?
Because from the 2 on the left side, it's constantly it's decreasing all the way down to 0. So on C, all of the y terms are below the x-axis, and then on the right side, they're all above.
Okay, good. Number 3, what does that match up with, platform?
You said D.
Okay, give me a little insight.
Because you are decreasing in the regular graph, so it has to be below the x-axis in the derivative graph until you hit 0, and then it starts increasing.
Okay. Okay.
And then
Okay. So do you notice how 1 and 3 are very similar graphs? Okay, I was trying to really make you think there about the order of the increasing and decreasing, right? Up until 0, 1 is increasing. Up until 0, 3 is decreasing. So you need to make sure that for number 3, up until 0, you have negative derivative values. Okay, so by process of elimination, where does 4 go? To A. All right? Huh. There must be some sort of connection with sine and cosine, huh? We'll have to talk about that later. Okay, so what I'm going to do is part of your homework is going to be a derivative graph match. So I'm going to hand this out, and I've shortened the, it's like a really long weather dress, so I shortened it with my Google account. But if you go to this website, they'll give you, I think it's 4 graphs, it's 3 or 4 graphs that you have to match up. Okay, and it'll tell you how many you got right. And you can do it over and over and over and over again for practice. I need to see one of those. Okay, so I'll give you a little bit more instruction here in a moment. I want to get back to our notes here. Okay, so here is the alternate form of the derivative. This is what will help you with numbers 51 and 52. Okay, so notice how we are still dealing with the slope, right? Now it's just y minus y over x minus x, as opposed to our denominator being more of like that change in x, okay? And specifically, we're looking at that certain c value, okay? Instead of taking the change in x and taking a limit towards 0, we're taking x minus c and we're bringing x and c closer together. So it's still, this is actually Thursday, the first graphic that I showed you, the first little, when I clicked through the slides and those points got closer and closer together. This is the first secant line that we looked at. Okay, so this is the slope of the secant line. The limit brings x and c close together, so we're still evaluating the derivative. But what's nice about this is we're evaluating the derivative at a coordinate instead of just evaluating the derivative and then plugging in 3 like we did this morning. Yes?
So that would be like if we did the problem of the day and you cut out like having us find the equation of the derivative and you're just like find it at 3 and we could use that.
We could, yes, you could. Now, if I had you finding it at 3 and 5 and 7, you wouldn't want to find 3 different derivatives, right? Okay, great question. So let's practice it. Our function is x squared plus 6x, and our x value is 2. Like Jackson said, if we're only finding it at one point, we could just use this definition if we're not worried about what the derivative function is. So we're going to take the limit as x approaches 2 of f of x minus f of 2. All over x minus 2. we plug in 2 to that equation, what do we get? Say it louder, I hear people whispering it. 16. Okay. Right now we cannot evaluate the limit because x minus 2 is in the denominator. But you know we are going to be able to with polynomial, right? So maybe we could factor our numerator. What is our numerator factor to? X plus 8, is that what you said? So then when we evaluate that limit, the derivative at 2 would be 10. Okay, so here's the deal. So 51 and 52 have been added to tonight's assignment. It is correct on the gold sheet, but it's not correct on here. Now I have little green slips of paper. Would you like me to hand them out, or would you like to just write it down? Hand them out just in case. Okay. But keep in mind that 51 and 52 are not on this green piece of paper. I didn't update it. Okay, that was my fault. I'm sorry. So this is what I need you to do. I need you to do the graph match and either print it out or email it to me. Okay? Now, I will say that it will not let you do the graph match on your phone, but what you could do is you can screenshot it and use like the drawing tools to match them up. You just won't get the feedback of if you're right or not. Okay? So if you want the website to tell you that you are right, you would need to do it on a computer. But you can do it on your phone and just like snap a picture, use the drawing tools to match them up, and then email that to me. Okay? So that's part of your homework, as well as the book work. Okay? Are there any questions?